Before we begin today's lesson, take a minute to do this warm-up problem. This is an investigation out of your textbook, and what it's asking is for several different variations of the same question, really. We have a coin toss, which they're going to call event A, and we have a die roll, which they'll call event B. So obviously A has two possible outcomes, heads or tails. B has six possible outcomes, 1, 2, 3, 4, 5, 6. And we're asked for a few different combined events. Let's just do the first one together. The probability of getting a head on the coin and a 4 on the die would be one way that can happen out of 12 possible outcomes. And then what they're asking for here, P of A, that's the probability of just the first event, so just a head on the coin toss. Well, there's a 1/2 chance of that occurring. P of B would be the probability of a 4 on the die roll. There's a 1 in 6 chance of that occurring, because 1 in 6 of the die outcomes would be a 4. So pause the video, fill in the rest of this table, and then answer question number 2. Hopefully you got these results for the table, filling in the different values for the intersection A and B, as well as for the individual events, the A and the B separately. As you look through this table, there's a pattern that connects the intersections here with the individual probabilities here. And that pattern is multiplication. 1/2 times 1/6 is 1/12. 1/2 times 1/2 is 1/4. And the same thing continues through the other rows. So to write this in general terms or in symbols, what we can do is to say that the probability of A and B, the intersection, is equal to the probability of A times the probability of B. Now this is a very important rule to remember. And will generally imply that you should multiply. There's a catch, as there often is. The catch is, notice in this problem, the two events A and B had nothing to do with one another. If you know the outcome of the coin toss, you can't make any prediction about the outcome of the die roll, and vice versa. What that means is that the two events are independent. If they were not independent, then we would need a modification here, because knowing that A had occurred would affect the probability that B occurs. So now let's look a little bit more at both of those cases, when they're independent and we can use this rule, versus when they're dependent and we have to do that modification. Let's look a little bit more at independent events. Remember again that an intersection is when both of the events occur, so this would be like an AND problem. Independent events are ones where the outcome of one does not affect the probability of the other, like in that first example. One way to think about this in symbols is if the two events are independent, then the probability that the second event occurs, given, remember this bar is conditional, given that the first event occurred, should really just equal the probability of the second event. If they're independent, then the fact that the second one occurred should have no impact. And for that matter, both of these things should also be equal to this right here. Do you understand what that means? This is the probability that the second event occurred, given that the first one did not occur. All three of these should be the same, whether the first event occurs, doesn't occur, or is just completely left out, should have no impact if the events truly are independent. Mathematically, what this means is that to find the intersection's probability, we just need to multiply. So this is what you found in that warm-up problem. Let's look at an example with independent events. Here we have two marksmen firing at a target simultaneously. This is important. What we're to deduce from this is that if they're both firing at the exact same time, then whether the first person hits the target or not shouldn't affect the second person, because the second person has already fired at the same time. So they're including this word to tell us that we should treat these events as if they are independent. They give us probabilities for each person hitting the target. And so let's just kind of define some variables here. Let's say that if Jiri hits 70% of the time, then this right here would be P of J, although of course we'll write it as 0.7. And if Benita hits 80% of the time, then this would be P of B, where B is the event that Benita hits the target, and that's going to be 0.8. So the first question they ask is, what's the probability that they both hit the target? In symbols, they could have written this as something like P of J and B, both successes. Since the events are independent, all we have to do is multiply those separate probabilities. 0.7 times 0.8 gives us 0.56, or 56% of the time that they will both hit the target. Moving on to the next one, pause for a minute and see if you can answer the remaining 3 questions by using the same logic. Look now at these results for parts B, C, and D. In each case, we're multiplying 2 different numbers based on who's hitting and who's missing. So something like J apostrophe would often be read as J not. And what that means here is that Jiri has not hit the target. Benita has not hit the target, so I've got both of those complement numbers. Jiri hits and not Benita, not Jiri and yes Benita, so we've multiplied these all out, gotten these results. Let me just say a few things about these results. First off, I didn't leave myself very much space here, but it would have been better if I had stated these answers as percentages. The only reason that really matters is because it would have matched what was stated in the original problem. So 56%, 6%, 14%, 24%. Another thing to notice is right here we've covered all 4 possible outcomes, and all of this adds up to 1 or 100%. If you were to think about a Venn diagram with the 4 distinct regions, let's say this circle represents all the times that Jiri hits the target. This circle represents all the times that Benita hits the target. Question A would refer to this region. Question B would refer to this region where they both miss. Question C, we're in the Jiri circle but not in the Benita circle, so that would be here. And question D refers to this region. So they should. This example leads to an important term that you should know. The 4 events that are created in parts A, B, C, and D, because they form the full sample space, they're said to be exhaustive. They exhaust all of the possible outcomes. All possible outcomes. That's a term you'll encounter sometimes. A question might ask something like, if it'll describe 2 events, can you prove that they are exhaustive? So just kind of know what that means. Let's look now a little bit more at the case of dependent events. With 2 dependent events, the outcome of one does affect the probability of the other, so you have to account for that whenever you're determining the probability of that intersection. You're still going to use multiplication. An intersection is still an AND problem and does still lead to multiplication. You just have to modify the second probability to take into account what happened with the first event. So here what we say is that the probability of A and B, the intersection, is equal to the probability of the first event. You account for that one, and then you multiply by the probability that the second occurs given that the first has occurred. So this is the change right here. It's still multiplication, but you take into account the impact that the first event had on the second. In a situation with dependent events, one thing you might just want to make a note of is that tree diagrams work very well. Just for organizing all the different numbers, you tend to have more numbers to keep track of on these problems because of all the different cases involved. Let's look at an example. Let's just extend actually that previous example. In the previous example, we said that Jiri had a 70% chance of hitting the target. Let's keep that. And we'll still call this P of J. But let's say that they're no longer going to fire simultaneously. Instead, Jiri's going to go first, and then whether or not he hits the target, maybe that would affect Benita. Maybe instead of having the same probability regardless, let's say she gets a little bit nervous, and so after Jiri fires, let's say that if Jiri hits the target, then Benita hits 50% of the time. And if he misses the target, then maybe she's a little bit more confident. Let's say if he misses J prime, then Benita hits the 80% that was given in the previous problem. Since we have more numbers to keep track of here, a tree diagram might help. For the first event, there are two possibilities. Either Jerry hits or Jerry misses. We know that this has a 0.7 chance and this has a 0.3. From there, for each of these, either Benita hits or Benita misses. So we have the same outcomes that can occur, but with different probabilities. If Jerry hits the target, then Benita has a 50% chance of hitting and a 50% chance of missing. If Jerry misses, then Benita hits 80% of the time, and that would mean that she misses 20% of the time, because these two need to add up to 100% for her portion. So then we get 4 different outcomes with 4 different probabilities, or I guess really just 3 different probabilities. A typical question might ask something like, find the probability that Benita hits the target. And this is no longer the simple 80% that it was in the original problem. Instead, recognize that there are 2 different ways that this can occur. One option is right here. Jerry hits and Benita hits. The other option is that Jerry misses and Benita hits. So to find the probability that she hits the target, we need to account for both of those. To get this probability, the probability that they both hit the target, we need to multiply along those branches of the tree diagram. 0.7 times 0.5 would give 0.35. Here, we're finding the probability that the first person misses and the second person hits. Multiply the probabilities. 3 times 8 is 24, so 0.24. So then the probability that Benita hits the target would come from 2 different possible outcomes. This one, or, so we'll add this one. We'll add the 2 different parts of the tree diagram, 0.35 for one possibility plus 0.24 for the other possibility. So we get a probability that she hits the target as being 0.59, or a better answer would be 59%, since the original problem was stated with percents. There are 2 more rules that you need to know at this point. These are both in the formula book, and they both apply to compound events or combined events. The first is called the addition rule, and it's for a union, meaning just putting 2 sets together, including the overlap. The rule here says that the probability of A or B, A union B, is equal to the sums of the probabilities of the individual sets. But you have to pay attention to that overlap. If you just add these 2 sets together, you count the overlap twice. We do want to count it, but we don't want to count it twice, so we'll subtract that duplicate. Subtract the probability of A and B. And this is what you're doing on the Venn diagram when you add up all the numbers in one circle plus all the numbers in the other circle. It's counting that overlap twice. So you subtract it once so that one counting of it will remain. And then also, a special case of this comes up if you have mutually exclusive events. Mutually exclusive events are ones where there's no overlap, meaning that the events can't both happen simultaneously. For example, if we're talking about drawing cards out of a deck, the event of drawing a 10 is mutually exclusive from the event of drawing a 6, because if you draw a single card, there's no way it can be both a 10 and a 6. So those would be mutually exclusive events. In that case, when you're doing this addition rule, there's no overlap to be subtracted, so the rule could be simplified this way. The probability of A or B is equal to the probability of A plus the probability of B. The overlap is a 0, so you can just leave that one out. It looks like a separate formula, but of course it's the same thing, just a special case of it. A Venn diagram for mutually exclusive events is going to have 2 disconnected circles. Often you don't know that at first. You'll begin with a Venn diagram that looks like this one up above, but then as you get to looking at the numbers, you'll find that this inner section has to be a 0, and so it could have been drawn separately. The last thing for today is to look at these two on your own problems. One of these has independent events and the other one has dependent events. So begin by identifying those.